Hello and welcome to Algebra 2 Lesson 9. In this video, we're going to continue to learn about applications of linear equations. So in this lesson, I want to go over 3 additional types of problems that you're going to encounter. We're going to take a look at mixture problems. We're going to take a look at some denomination of money problems. And we're also going to take a look at some motion word problems. So before we get started, let's revisit our kind of guidelines for solving a word problem when you have to set up and solve a linear equation in one variable. So the first thing you want to do is read the problem and determine the question or questions to be answered. Then we want to assign a variable to represent the unknown. And if you have more than one unknown, you're going to represent other unknowns in terms of that variable. Then we want to write an equation. Then we're going to solve the equation. We're going to write the answer in terms of the question or questions being asked. And then lastly, we're going to check the answer using the words of the problem. And again, the main thing with checking the answer is to make sure that it's reasonable. I always use an example where I say, if you're asked to find the number of people on a bus or a train or a car, and you get like negative 4.3, you know you did something wrong, right? You're not going to have a negative amount of people on a bus. At this level, when we talk about linear equations in one variable, our mixture problems will involve basically rates of concentration. So let's read through this real quick. This is a nice little starter problem for us. It's going to teach us how to find the concentration of a substance. So an alcohol solution was made by mixing 3 gallons of an 80% alcohol solution and 4 gallons of a 52% alcohol solution. Find the concentration of the new mixture. So how do we go about doing this? Well, what I want you to do is take a piece of paper and a pencil out if you don't already have one. And I want you to write this down. Let me go to a different page. If you want the concentration of a substance, so concentration of the substance, this would be equal to, you need the pure amount of the substance, and this is over or divided by the total amount of the mixture. So once you understand this right here, it's going to be really easy for you to do these mixture word problems. I can't tell you how many students I've tutored and they don't even understand this and they're trying to solve the problem. You have to know how to get the concentration of the substance before you can do anything. So let's go back up and we're going to fill in this information here. Now the information we're given is that there's 3 gallons of an 80% alcohol solution and 4 gallons of a 52% alcohol solution. So let's use this down here. So if I've got 3 gallons of, again, an 80% alcohol solution, how much pure alcohol is that? Well, I basically just take 3 and I multiply it by 80% or 0.8 as a decimal. So 3 times 0.8 gives me what? Well, 3 times 8 is 24. And I have 1 decimal place between the two factors. So this is 2.4. And think about your units there, it would be gallons. So basically, 3 gallons of an 80% alcohol solution is 2.4 gallons of pure alcohol. So when we think about the pure amount of the substance, again, from this, I'm going to have, let me just write it right here. I'll have 2.4 going in there. So let me erase this real quick. And I'm going to put my fraction bar. And then in here, total amount of the mixture, I know this came from a 3-gallon mixture. Now I'm going to add to this, and I'm going to add to this. Remember, we had another part. We were mixing this with 4 gallons of a 52% alcohol solution. So 4 times 52% as a decimal is 0.52. 4 times 52 is 208. You've got 2 decimal places between the factors, so this is 2.08. So again, this is how much in gallons that we have as a pure amount of alcohol. So this goes up here, 2.08, and the total mixture is 4 gallons. So that goes here. So what do we have in the numerator? Again, we have the pure amount of alcohol from the first mixture plus the pure amount of alcohol from the second mixture. So the numerator is the pure amount of the substance. In this case, it's alcohol. So 2.4 plus 2.08 gives me 4.48. And this is over the total amount of the mixture. The first mixture was 3 gallons in total. The second mixture was 4 gallons in total. So 3 plus 4 would give me 7. Now, all we need to do is crank this out. So 4.48 divided by 7 is 0.64. So you can erase this and put 0.64. And we know as a percentage that's 64%. So let's go ahead and answer this with a nice little sentence. Find the concentration of the new mixture. The new mixture is 64% alcohol. AlCOHOL. And it's really that simple. This is a very easy problem. I mean, you just go through the kind of formula that I gave you, but make sure you have that written down because a lot of times you're going to need to know how to find the concentration of a certain substance that comes from, mixing one or more items. All right, so now let's take a look at one that's a little bit more challenging. So Jennifer asked you to make 12 gallons of fruit punch that contains 48% fruit juice by mixing together Betty's fruit juice and Calvin's fruit juice. Now, Betty's fruit juice is 38% fruit juice, while Calvin's fruit juice is 53% fruit juice. How many gallons of each are needed? So a lot of times with mixture problems, we get very, very confused on what we need to do. I want you just to think about the fact that in the end, I want a 12-gallon mixture that is 48% fruit juice. So that's the goal. So let's write that down here. Our goal is 12 gallons that is 48% fruit juice. So how are we going to get that? Well, we've got to use Betty's fruit juice and we've got to use Calvin's fruit juice. We don't know how much of each we're going to use. But we do know that we're going to take a total of 12 gallons for the mixture. So this is my total mixture. In gallons. So if I let X be equal to the number of gallons of, let's say, Betty's fruit juice and we'll put used, then what can I say about the amount we're going to use from Calvin's fruit juice? So then, well, if this is in terms of gallons and it's the whole amount we're using, remember the total mixture is 12 gallons. So whatever I use here can be subtracted away from 12. In other words, if I had 12, the total number of gallons from this mixture in the end, minus X, the number of gallons we're using from Betty's fruit juice, well, that's got to give me the number of gallons of Calvin's fruit juice used. And of course, you could have reversed that and said X is the number of gallons of Calvin's fruit juice used, and then 12 minus X would have been the number of gallons of Betty's fruit juice used. Doesn't matter. You'll get the same answer either way. Now, how do we go about making an equation? We've got our unknowns expressed with some variables. How do we make an equation? Well, the one thing is that we know that in the end, the amount of pure fruit juice from Betty's fruit juice plus the amount of pure fruit juice from Calvin's fruit juice has to equal the amount of pure fruit juice in the goal mixture. So in other words, we know that Betty's fruit juice is 38% fruit juice. So if I use 0.38, that's 38% as a decimal, and I multiply it times x, this is the pure fruit juice. And this is from Betty's. Now, if I add this to, and I'm going to do the same thing for Calvin's fruit juice. So if I add this to, his is 53% fruit juice, so 0.53 is a decimal, times this quantity, 12 minus x. This is the pure fruit juice. And in this case, it's from Calvin's. If I sum these two amounts together, it's got to be equal to the amount of pure fruit juice in the end mixture. So in other words, it would be 12 times 0.48. And this is the pure fruit juice in the final mixture. Because again, the final mixture comes from these two inputs. So this has to be true. So once we have our equation set up and we understand the logic behind it, we just need to solve it. We will figure out what x is. That'll tell us the number of gallons of Betty's fruit juice used. We can then plug in for here and find out the number of gallons of Calvin's fruit juice used, and we've solved our problem. All right, so to solve this, we'll have 0.38 times x plus, if I use my distributive property, 0.53 times 12 is going to be 6.36. Then minus 0.53 times x is 0.53x. And this equals 12 times 0.48 is 5.76. All right. So if we combine like terms here, 0.38x minus 0.53x is negative 0.15x. And then we have plus 6.36, and this equals 5.76. Of course, I will subtract 6.36 away from each side of the equation. So that's gone. And I'll have negative 0.15x is equal to 5.76 minus 6.36 is equal to negative 0.6. So now as a final step, we divide both sides of the equation by negative 0.15. And what's going to happen is this will cancel with this, and I'll just have x, and that's equal to negative over negative is positive. 0.6 divided by 0.15 is 4. So x here equals 4. Now, so remember, x was the number of gallons of Betty's fruit juice used. So we're going to use 4 gallons of Betty's fruit juice, and then 12 minus 4, or 8 gallons of Calvin's fruit juice. So we can say we need 4 gallons of Betty's fruit juice along with 8 gallons of Calvin's fruit juice. And to check this, we would think about our equation that we set up. Let's scroll down a little bit. And again, the amount of pure fruit juice from Betty's fruit juice plus the amount of pure fruit juice from Calvin's fruit juice has got to be equal to the amount of pure fruit juice in the final mixture. So if I just plug in a 4, everywhere I see an x, I can just make sure the left and the right side are equal, and I'm going to be good to go. So 0.38 times 4 is 1.52. 0.53 times 8 is 4.24. And 12 times 0.48 is 5.76. Now, if I sum these two right here, I do get 5.76. So you get the left side equal to the right side. And it's more important here to understand why they're equal. Again, this right here tells me the total amount of pure fruit juice in gallons that I'm going to have from these two inputs. I've got 1.52 gallons coming from Betty's fruit juice, and then I have 4.24 gallons of pure fruit juice coming from Calvin's fruit juice. So again, the sum of that is 5.76 gallons of pure fruit juice. And that's what I want. Because in my final mixture here, I've got 12 gallons total. That's 48% pure fruit juice. So it's 5.76 gallons of pure fruit juice in the final mixture. So because these two sides are equal here, we know we found the correct answer. Again, we're going to use 4 gallons of Betty's fruit juice along with 8 gallons of Calvin's fruit juice. All right, let's take a look at the next one. So for a bill totaling $1,105, a clerk received hundreds, 20s, and ones only. There were 6 times as many 20s as hundreds, and 25 fewer ones than 20s. How much of each type of bill was received? So again, for this type of problem, once you read it and you understand what you're being asked, which let's just go ahead and highlight that, how much of each type of bill was received, you're immediately thinking about what to do in terms of setting up your variable. Now, if you have 3 things you need to figure out, how many hundreds, how many 20s, and how many ones, you really need to think about what's going to be easiest for you to use. And again, I keep talking about this in these videos. If you have something that's used in each comparison, then you want to use that because it's easier to model things. So if we say that there were 6 times as many 20s as hundreds and 25 fewer ones than 20s, well then the amount of 20s that were received, or the amount of $20 bills that were received, that's used in each comparison, so it's easiest to just let the variable, like x, be equal to that. So let's let x be equal to the number of 20s received. So then what can we say about the hundreds? So it says here there were 6 times as many 20s as hundreds. So that tells me that when I think about the number of hundreds, it's 1/6 the amount of 20s. So then we can say that 1/6 times the number of 20s received, which we represent with x, is equal to the number of hundreds received. Then what can we say about the number of ones? Well, it says that there were 25 fewer ones than 20s. Well, if the number of 20s received is represented with x, then we could say then literally x minus 25 would be equal to the number of ones received. So now that we've represented each type of bill, we want to think about making an equation. And what it tells us here is that the bill totaled $1,105. Now, a common mistake with these type of problems is just to take what you modeled here and say, okay, well, x plus 1/6x plus x minus 25 is equal to 1,105. That's not going to get you there because remember, this is a value. This is the value. This right here gives you the quantity of bills in each case. X gives you the number or the quantity of $20 bills received. That's just a number. If I hand you 4 $20 bills, that's not a value. You're just saying, hey, I have 4 of them. You've got to multiply the 4 times the value per bill. If it's 20s, then 4 times 20 would give you 80. I've got $80. So you've got to match up the information on the left with the information you're given on the right. So for each type of bill, you got to multiply it by the value. So for the 20s, which is represented with x, I'm going to put 20 next to it. So this is the value, and this is the number of bills. Again, I go back to the example. If I hand you 4 $20 bills, if you plugged in a 4 there, 4 times 20 would give you 80. You know you have $80 there. For the number of hundreds, I've got 1/6x, multiply that by 100. And for the number of ones, I've got x minus 25. that quantity, make sure you use parentheses. Let's multiply that by 1, okay, by 1. And you know 1 times anything is just itself, but again, you want to just use parentheses so you get in a good habit of things. All right, so now let's solve this equation. We would have 20x plus 100 times 1/6. Well, we know they're each divisible by 2. This would be 50. This would be 3. So let's put 50 over 3 times x. Then plus, I can just drop the parentheses here. This is just x minus 25. This equals 1,105. All right, let's scroll down a little further. So 20x plus x is 21x. And then we have plus 50 thirds x. And then minus 25 equals 1,105. Let's add 25 to each side of the equation. That will cancel. And we'll have 21x plus 50 thirds x is equal to 1,105 plus 25 would be 1,130. I've got a fraction here. I can multiply both sides of the equation by 3. Or what I can do is I can multiply this by 3 over 3 and I can just work with the fractions. It doesn't matter. Typically we just clear the fractions, so let's just do that. Let's multiply both sides of the equation by 3. 3 times 21 would be 63. So this would be 63x plus 3 times 50 over 3 would be 50. So this would be 50x. And this equals 1,130 times 3. Well, if I think about 3 times 1,000, that's 3,000. 3 times 100 is 300. 3 times 30 is 90. So that would be 3,390. All right, so let's continue now. 63x plus 50x, 3 plus 0 is 3. 6 plus 5 is 11. So this would be 113x equals 3,390. Divide both sides of the equation by 113. And we'll find that x is equal to 30. Okay, this cancels with this, and we got 30. Again, we're working with a word problem, so let's make sense of this. Again, if x is the number of $20 bills received, and x equals 30, then I know I got 30 of these. And again, if you want to just check things, 30 times 20 would be 600. So the value from the 20s would be $600. Then for the number of hundreds received, it's 1/6 times 30. 30 divided by 6 would be 5. So they got 5 of these. The value would be $500. And then x minus 25 is the number of ones received. 30 minus 25 is 5. So this is 5. So this would be $5. And that's consistent with what we're given in the problem. 600 plus 500 is 1,100. 1,100 plus 5 is 1,105. Again, for a bill totaling $1,105. So we can just state that the clerk received 30 $20 bills with 5 $100 bills and 5 $1 bills. So again, the clerk received 30 $20 bills with 5 $100 bills and 5 $1 bills. And again, easy to check. 30 times 20 is 600, so that's the value from the 20s received. 5 times 100 is 500, so that's the value from the $100 bills received. And 5 times 1 is 5, the value from the $1 bills received. So 600 plus 500 is 1,100. 1,100 plus 5 gives you this, 1,105. Again, the total bill that we're told in the problem. All right, so let's take a look at the next one. And now we're going to talk about motion word problems. So we saw these in Algebra 1, and these use the formula distance equals rate of speed times time traveled. So if I'm in a car and I'm going 30 miles an hour for 7 hours, I multiply 30 times 7, that gives me 210, and I know I went 210 miles. So a passenger plane left Rome and flew south. 2 hours later, a cargo plane left from the same location and flew 80 miles per hour faster in an effort to catch up. After 7 hours of flying, the cargo plane caught up. What was the passenger plane's average rate of speed in miles per hour? So for this one, again, we're going to use our distance formula. So distance is equal to rate of speed times time traveled. Okay, this is abbreviated with D equals R times T. Very common formula, very common type of problem. So the first thing we want to do, again, let's go back up. We understand that the question here is, what was the passenger plane's average rate of speed in miles per hour? Now, to get this, first we need to figure out what we need to do to model this. And typically you'll say, let's let x be equal to what you're looking for. Well, we're looking for, again, the passenger plane's average rate of speed in miles per hour. So let's do that. So let's let x be equal to the rate of speed for the passenger plane. Okay, so once we've established that, let's talk about the cargo plane's rate of speed. So what does it tell us about that? Well, it tells us that the cargo plane left from the same location and flew 80 miles per hour faster. It doesn't tell us its exact rate of speed, but however fast the passenger plane is going, the cargo plane is going 80 miles per hour faster. So then I can say then x, which is the rate of speed of the passenger plane, plus 80 would be equal to the rate of speed for the cargo plane. So you might be thinking, okay, we've got this kind of set up. How in the world are we going to get an equation going? Well, what do we know here? Let's make a little table. I often don't make tables because in a lot of cases you don't need them. But with a motion word problem, they really help you organize things. So let's do distance equals rate times time like this. We'll make a nice little table. We have two scenarios. So we have our passenger plane. And we have our cargo plane. Now, the rate of speed we know already. For the passenger plane, the R, we've modeled it with x. That's easy enough. For the cargo plane, we know it's x plus 80. Now, does it say anything in the problem about the time? Well, yeah, it kind of does. A passenger plane left Rome and flew south 2 hours later. So that means that the passenger plane is traveling for 2 hours more than the cargo plane does. So 2 hours later, a cargo plane left from the same location and flew 80 miles per hour faster in an effort to catch up. After 7 hours of flying, so let me just stop there. The cargo plane flies for 7 hours at the point where they catch up and the problem kind of stops, okay? The passenger plane, again, it tells us, because of this 2 hours later thing here, was flying for a total of 9 hours. So 9 hours for the passenger plane, 2 hours less for the cargo plane, 7 hours. Let's go back down. Let's fill in the information here. For the passenger plane, it's 9 hours. For the cargo plane, it's 7. Now, I want you to realize something. They didn't tell us a distance. But if I have a rate of speed and I have a time, I have a distance because I just multiply the two together. If my rate of speed is 30 miles per hour and my time is 7 hours, 30 times 7 is 210. I know my distance, right? It's 210 miles in that case. It's the same thing here. I have a rate times a time. So 9x is the distance. I have a rate times a time. So 7 times the quantity x plus 80 is the distance. You might say, okay, well, that's great. How do we get an equation? Well, there's one thing that you might have missed out on here. Let me go back up. And let's read through the problem one more time. What could you see that's equal here? Again, a passenger plane left Rome and flew south. 2 hours later, a cargo plane left from the same location. So they leave from the same location and flew 80 miles per hour faster in an effort to catch up. After 7 hours of flying, the cargo plane caught up. So that means they end at the same location. They start at the same location. They stop at the same location, where the problem kind of stops at the same location. You might as well say that. But for the sake of the problem, they went the same distance. So that means the distance that the passenger plane went is the same or is equal to the distance that the cargo plane went. Now coming back down here, I know what the distance is for each one. So voila, I've got my equation. Because all I have to do is set this distance, which is 9x, equal to this distance, which is 7 times the quantity x plus 80, and I can solve my equation for x. So use my distributive property over here on the right. 7 times x is 7x, plus 7 times 80. We do 7 times 8, that's 56. Put a 0 at the end, that's 560. We would subtract 7x from both sides of the equation. That cancels. You'll have 2x is equal to 560. Divide both sides of the equation by 2. And what's going to happen is this will cancel with this. I'll have x is equal to 560 divided by 2 is 280. So what does that tell me? Let me go back up. X was the rate of speed for the passenger plane. So that tells me that the passenger plane was traveling at 280 miles per hour. So the passenger plane was traveling at 280 miles per hour. That's their average rate of speed. How do we check this? Well, it's actually pretty easy. If I take 280, which is the rate of speed, and I multiply it by 9, which is how long the passenger plane travels for, I get 2,520. That's the total number of miles that the passenger plane traveled. Now, with the other guy, the cargo plane, it goes faster. 280 plus 80 is 360. So that's its average rate of speed in miles per hour. It does it for 7 hours. If you multiply 360 by 7, you also get 2,520. So the mileage syncs up there. They traveled the same number of miles, so the distances are equal when we check them, so we know I have the correct answer. The passenger plane was traveling at 280 miles per hour.